Once I decided that I wanted to engineer enzymes, I sat down and realized, after a couple tough years, that nobody had a clue how to do that, right? We know how to manipulate the sequence, but that's very different from being able to make something that's better than what nature had already made, or at least works in a completely new environment. When you don't know what to do, it's always a good idea to look around and see what works. So of course I looked at the human methods. The structural biologists said, oh, you get the structure of the enzyme and then you go in and you manipulate it. Well, that method didn't work. But there's another method out there that's worked for about 3 billion years, and that's called evolution. Evolution can go in very strange directions. But I decided to make an enzyme that's often used in laundry detergents, a protease, make it function in a highly non-natural environment, dimethylformamide, a really polar solvent. And there were biochemists who told me that's impossible, an enzyme would never work, in dimethylformamide. And then others said, well, that's stupid. Who cares about an enzyme that works in dimethylformamide? And I just said, well, let's just see what happens. Let's see if we can make enzymes work in these highly non-natural environments. And sure enough, the enzyme learned very quickly how to tolerate very, very high concentrations of that solvent. So there were two camps of adoption. One was, oh, that's not science, so we're not going to do that, right? That was the academics. But the other camp was, oh my goodness, she solved this really hard problem in a few months without any crystal structure. And so everybody in industry, for example, who had interesting problems that they wanted better enzymes for, they started coming to me. And one after another, we would solve tough problems. Well, the targeted design is where do you start and what properties are you interested in? But the actual enzyme design doesn't have to be targeted. But you don't have to know how the enzyme works. You don't have to know where the beneficial mutations are. The system tells you those rules. And that's what I love about it, because when you let the system tell you what matters, you actually learn something that you didn't know before. These combinatorial methods were evolutionary methods, and my co-winners of the Nobel Prize, for example, designed peptides. They would make millions of peptides in a single experiment and then pan them, sort them by binding. You can't do that with an enzyme. So all the products of evolution have provided a huge database of how does the sequence encode function. And we saw how the AlphaFold used that database of sequence and structure that human beings have deposited, right, into this database, how that used it to basically build models that would predict the structures of a protein given the sequence. The next big frontier is to predict function of a protein given the sequence, or even better, given a function, what is the sequence that does that? We're still a ways away from doing that with enzymes, but not too far. And especially given directed evolution's ability to take something that's kind of lousy and turn it into something that's beautiful and useful, if AI can generate the lousy starting point for something we can't find in nature, for example, then we have the problem solved. Because you can use AI and combine it with these evolutionary methods to really pretty quickly generate enzymes for, I would hope, virtually any chemistry.